So, when you're picking a sharding key, it's crucial to think about the access patterns and how evenly they distribute across shards. You don't want to end up with uneven load distribution.
That makes sense. But what if your initial assumptions about access patterns change over time?
True. That's why it's important to choose a key that can handle variability. For instance, using something like user ID can be safer than date or region because users tend to have consistent interaction levels.
I see. But isn't there a risk of hotspots even with user IDs if certain users become more active?
Absolutely. And that's where secondary keys come into play. Sometimes combining multiple attributes helps spread the load better. Like adding timestamp to user ID could help manage sudden spikes in activity for specific users.
Combining keys sounds complex though. How do you decide which attributes to combine?
It's definitely tricky. The key is understanding your application's usage and data flow well. Also, having a flexible schema design allows easier adjustments down the line. And hey, remember that pottery wheel? Just like how we adjust speed and pressure here, you tweak your sharding strategy based on real-world performance data.
That's an interesting analogy. I guess it simplifies thinking about dynamic adjustments.
Exactly. Plus, monitoring tools are vital. They give insights into whether your current strategy still fits or needs tweaking. Oh, look at that pot. See how symmetrical it turned out. Similarly, balanced shard loads ensure smooth operations.
Monitoring tools make sense then. They provide the feedback loop needed for continuous improvement.
Precisely. And let's not forget the importance of scalability too. How easily new shards can be added without disrupting existing ones. This often comes back to the database architecture and how smartly it handles partitioning and rebalancing content.
Scalability is critical indeed. It seems like choosing the right sharding key is just one piece of a larger puzzle involving architecture and ongoing management.
Indeed, it's all interconnected, just like these pieces of clay coming together to form this beautiful vessel. Exactly, it's all interconnected. Speaking of which, have you ever thought about horizontal versus vertical partitioning methods? Each has its pros and cons depending on the use case.
I have, but I'm always curious about your take on it. What are some scenarios where one might be preferable over the other?
Horizontal partitioning is great when you need to scale out by splitting rows across different nodes. Think of it as spreading data across multiple tables based on a key, like sharding we were discussing. It's particularly useful when you have large datasets and need to improve query performance by reducing the amount of data scanned.
That makes sense. So, horizontal partitioning is more about distributing the load evenly across nodes.
Exactly. On the flip side, vertical partitioning involves splitting columns instead of rows. You'd separate different types of data into distinct tables or even databases. This is handy when certain parts of your data have very different access patterns or require different levels of security.
Right, so vertical partitioning can help with optimizing storage and query efficiency for specific data types.
Absolutely. And let me tell you, deciding between them isn't always straightforward. It depends heavily on your application's requirements and how your data is accessed. For example, if you're dealing with financial transactions that need high security for sensitive fields, vertical partitioning might be the way to go.
I see. So, each method addresses different aspects of scaling and optimization.
Precisely. And remember, it's not mutually exclusive either. You can mix both approaches depending on what works best for your system. Just like blending techniques here at the pottery wheel to create unique shapes. Exactly, mixing both approaches can be quite effective. Speaking of which, another technique that's really useful for load balancing is consistent hashing. Have you had much experience with that?
I've read about it, but I'm still trying to fully grasp how it works in practice. Could you explain a bit more?
Sure thing. Consistent hashing is designed to handle the dynamic addition and removal of servers, while keeping the number of keys that need to be remapped minimal. It uses a hash function to map each server and data item onto a circle or ring.
A ring? That sounds interesting. How does that work exactly?
Imagine a circular space where each point represents a possible hash value. When you add a new server, you place it at a particular point on this circle. Then, when you want to store or retrieve an item, you hash its key and find the next node clockwise from that hash value.
So, the position on the ring determines which server gets the data?
Yes, exactly. The beauty of this approach is that if you add or remove a server, only the items near the removed or added node need to be remapped. This minimizes disruption, compared to traditional hashing methods where removing or adding a server would cause a lot more rehashing.
That makes sense. It seems like it would provide a more stable environment for handling data distribution.
Absolutely. And it's particularly useful in distributed systems where nodes might come and go frequently. Another neat aspect is replication. By placing virtual copies of each server around the ring, you can ensure redundancy and fault tolerance.
Replication through virtual copies sounds like it could enhance reliability significantly.
Definitely. Plus, consistent hashing helps balance loads more evenly because each segment of the ring corresponds to a server's share of the data. It's like ensuring every part of this clay pot is shaped equally as we spin it on the wheel. Exactly. Consistent hashing helps keep things balanced and reduces disruptions. Now, let's talk about how sharding impacts database performance. Have you noticed any significant differences in performance after implementing sharding?
I've seen improvements, but it also seems to introduce some complexities. Can you elaborate on the pros and cons?
Sure. One of the biggest advantages of sharding is improved query performance due to reduced dataset size per shard. When queries are confined to smaller subsets of data, they execute faster. Additionally, it allows for horizontal scaling by adding more shards as your data grows.
That makes sense. But what about the downsides?
Well, managing multiple shards can get complicated. Coordinating transactions across different shards requires careful planning to avoid inconsistencies. Also, certain types of joins and aggregate queries can become slower if they span multiple shards.
Right, coordinating across shards sounds challenging. Are there ways to mitigate those issues?
Absolutely. Using a distributed transaction manager can help maintain consistency across shards. For query performance, indexing strategies and caching mechanisms can significantly reduce latency. And let's not forget that proper load balancing through techniques like consistent hashing ensures that no single shard becomes a bottleneck.
Proper indexing and caching sound like good practices to keep in mind.
Definitely. And remember, the key is to strike a balance, optimizing for both read and write operations while keeping administration manageable. It's a bit like refining this pottery piece, fine-tuning each aspect to achieve the best results.
Balancing all these factors must be quite intricate.
It certainly is, but with the right strategies and tools, it's possible to achieve significant performance gains while maintaining system stability.